Hello, good morning dear students. Okay, this is Khadar handling JEE and NEET classes of E4U. Today we are going to discuss very interesting topic from the physical chemistry of class 12th, that is solutions. Okay, now let us start with here what are the content sheet is given here. Okay, introduction and very important concentration terms. Okay, next one solubility, how it will be, okay, the solubility nature in solid and as well as solid in liquid type of solution, and okay, gases in liquid type of solution we are having the law, Henry's law. Next one vapor pressure and factors affecting. Next one vapor pressure of liquid type of solution we are having the one law, that is known as here Raoults law, and the vapor pressure of solids in liquid type of solution. Okay, and okay, very important types of solution, ideal and as well as non-ideal solutions, and okay, very important property, that is colligative, relative lowering in vapor pressure and elevation in boiling point, depression in freezing point, and finally osmotic pressure. And very important, finally we have to calculate the water factor by using here abnormal colligative properties. Now let us start with here our okay, topic solutions. Now first of all, before going to discuss this one, first of all we want to understand here, sir, what is meant by here solution and what type of components which is present here. Okay, first of all, is it a solution is a one type of mixture. Okay, we are having the mixture homogeneous and as well as heterogeneous mixture is there. Okay, now if you take it solution which is comes under homogeneous or heterogeneous mixture, dear students, here very important and very okay important thing, that is solution which comes under here, it is a one type of mixture, that is called as homogeneous mixture. Okay, now we can define the okay solution. Okay, a homogeneous mixture of two or more okay components or substances okay whose okay composition may be varied with certain limits, at particular limits only, then it is known as a solution. Okay, why we are calling use the last term which is variable with certain limits. That means here if you raise the temperature, the properties of the mixture will be changing. If you raise the okay temperature, pressure, something, that's why we have to call it is a homogeneous mixture. One more time, a homogeneous mixture of two or more components whose composition may be varied with a certain limits, that is known as here solution. Now we understood here solution which is comes under okay homogeneous mixture but not heterogeneous mixture. And what are the okay components will come here, solution which is equal to here, already we studied in the lower classes, solute plus solvent, solute plus solvent. Okay, now let us start here. What is meant by solute? Already we know the component of the solution which is dissolved in the solvent is known as here solute. Generally solute which present in the solution is very less quantity. Less quantity is present. Next one, what is meant by here solvent? The component of the solution which dissolve the other component in it is known as here solvent. Generally in a solution okay a large amount or okay more quantity of the okay solvent is present. For example, if you take it here okay, if you take it the sugar in water, sugar in water, if you generally if you take it here okay in that for example, this is I am considering 50 ml of water, 50 ml of water. Okay, how much amount of the sugar generally you are using here? Okay, 20 grams of sugar I am adding. That means here this is known as here 20 grams of the sugar, generally less quantity, that is called as solute. Generally more quantity, that is called as here okay no, that is called as here solvent. More quantity here, what is dear students, less quantity, the solution which is equal to here solute plus solvent. Okay, next one, based on the okay, classification which is mainly based on the solute, we are having the types of solution, that is saturated, unsaturated and supersaturated solution, already you studied. Okay, next one, based on the solvent we are having okay or based on the concentration or the based on the number of moles of the solute, we are having the two types of solution. One is called as dilute solution, second one is concentrated solution. Dilute solution, if you go to lab okay laboratory chemistry lab, we will be observing DIL-HNO3 or CONC-HNO3, like that they will be mentioned. Okay, dilute, that means here dilute solution, dear students, Dilute means, okay, which one is the more quantity here? Okay, large quantity will be water, that is correct or not? Okay, and less amount solute will be present, either it is NaCl or NaOH, anything. This is comes under what, my dear students? Solvent. Okay, next one, if you take it at the same time, what is the concentrated solutions are? Is everything is reverse. Okay, take it here, less amount of water and more concentrated or more amount of here solute. This is solvent will be less amount, okay, solute will be more amount. Such type of solution called as here concentrated solution. Next one, classification which is based on the solvent, we are having the aqueous solution and as well as okay, non-aqueous solution. Aqueous solution, water is acts as a solvent, that is known as aqueous solution. Okay, generally we used to take it generally considering aqueous solution of NaOH, aqueous solution of glucose, aqueous solution of NaCl, like that we are considering. Next one more time, that is called as a non-aqueous. Other than water is act as a solvent, such as carbon tetrachloride, chloroform, benzene and dimethyl ether or diethyl ether. This all comes under non-aqueous solutions. Okay, dear student, and very important, next we can comes under here concentration. The methods of expressing the concentration of the solution. Already we know the concentration generally how to define, dear students. Okay, concentration we can mention here, C is equal to N is divided by V. Understand? The concentration of the solution is defined as the number of moles of the solute is dissolved in the unit volume of the solution is known as here concentration. For example, V I can consider here 1 liter. Okay, then what will happen, dear students? C is equal to N or not? Okay, now how can I define here? The number of moles of the solute is present or dissolved in 1 liter of the or unit volume of the solution is known as here concentration. Then what are the units? Already know the units of the concentration is here moles and volume in liters, that is moles per liter. This is about what, my dear students? Concentration. Now we are having the some different types of concentration methods. One is known as here mass percentage, volume percentage, mass by volume, ppm, molarity, normality, molality, mole fraction, and finally okay, formality. This is a very important. Just I am writing the formulas. Okay, you can study. First of all, we are having the mass percentage. Mass percentage, dear student, generally the weight of the mass of the solute is dissolved in 100 grams of the solution is known as here mass percentage. Generally I am writing here weight of or mass of solute is divided by weight of solution into 100. Generally how to represent here? Okay, weight percentage or mass percentage is equal to here, okay, W2 is divided by W1 plus W2 into 100. Okay, this is the mass percentage. Understand? That means just I check weight of the solute or mass of the solute is dissolved in 100 grams of the solution known as here weight or mass percentage. Next one, what are the units are? Very very important, dear students. Units must remember. Okay, now units, no units, because we just if you take it here weight in grams, grams is divided by okay grams, both are cancelled here. Okay, for number there is no units, and very important here it is temperature independent, because if you raise the temperature, okay, the mass, the quantity of the mass will not be changed, will not be altered. That is first one. Okay, next one comes under here volume percentage. Volume percentage also the same thing, dear students. The volume of the solute which is dissolved in okay 100 milliliters of the solution is known as here okay volume percentage. Directly I am writing the formula, V2 is divided by V1 plus V2 into 100. Okay, this is the volume percentage. Again I am telling here the volume of the solute is dissolved in 100 milliliters of the solution known as volume percentage. And comes under here what are the units? Units here also same. I can consider here milliliters into 100, both cancel here. There is no units for volume percentage. Next one, will it depends on temperature or not, sir? Just have a check it here. Okay, whenever the volume factor is there, temperature is dependent. Okay, here temperature is dependent. Okay, why? The volume of the solution which is inversely proportional to okay, or sorry, it is directly proportional to temperature according to Charles law. Then V1 by T1 is equal to V2 is divided by T2. According to Charles' law, volume directly proportional to its absolute temperature. So it is depends on temperature. Next one comes under here, mass by volume percentage. Mass by volume percentage, same. The mass of the solute which is dissolved in 100 milliliters of the solution, commonly it is called as here mass by volume percentage. Generally we have represent here W by V into 100. This is the formula for dear students, mass by volume percentage. Next one, sir, what about the units, sir? Will it depends on unit? Units, just have check it here. What is this one? For example, if you take it the grams per milliliter, also you can consider here. Understand? Next one, will it depends on temperature, dear students? Here temperature, it is temperature dependent. Why? There is a volume factor is there. Next one comes under very important ppm, parts per million. Parts per million. For example, if you want to measure or if you want to calculate very smaller amount or a traces quantity of the solute is present in the atmosphere, then with the help of parts per million we have to calculate. For example, if you take your bike, after you start that bike, how much amount of the carbon dioxide gas or how much amount of the pollution is present in the atmosphere, how can you calculate? You can't able to hold, sir, 1 kg of the pollution came from my bike, sir, we can't tell because it is present in very less quantity of amount. That's why we have to mention here in terms of parts per million, ppm. Then ppm is equal to, generally how to represent here, the number of parts of the components, number of parts of the components in the solution, components in a solution divided by total number of parts of the components in the solution, total number of parts of the component in the solution. Here million, that means what, my dear students? Here 10 power 6. This is the formula for ppm, number of parts divided by total number of parts of the solution into 10 power 6. This is 10 power 6. This is called as ppm. Next one comes under very important, that is known as here molarity, capital M. Don't get confused, dear students. Molarity, RITY, that is M. Now molarity, generally how to represent, how to define here, the number of moles of the solute is dissolved in 1 liter of the solution is known as here molarity. Generally how to represent here, capital M is equal to N is divided by volume in liters. That implies how to do it here, capital M is equal to, I can write how to calculate moles, given mass by molar mass, I can write it a gram molecular weight or mass into, in terms of milliliters, if I take it here 1000 by volume in milliliters. Now what are the units of this molarity, sir? Units of this molarity, here N stands for here number of moles. Next one, volume in liter, that is moles per liter. Sir, will it depends on temperature or not, sir? Obviously, because there is a volume factor is a temperature is dependent. Temperature is dependent. This is the one type. Next one, if you take it here, there are two solutions are there, solution 1 and as well as solution 2. Then how to the first solution having its molarity is M1 and its volume becomes here V1. Then after you dilute, dilute condition this is. After you dilute, what will happen, dear students? The molarity will change or not? Yes, obviously it will change from M1 to M2 and the volume also will be changing because after you are adding the water, that is called as a dilution. And volume also will be changing from V1 to V2. Then how to give the relation between these two? M1 V1 is equal to here M2 V2. This is the very important relation, dear student. This is for dilute solution. They will give the 3 values here, then we have to calculate the volume K1 or volume 2 or else you can calculate the second molarity or first molarity based on the given data. This is the temperature dependent moles per liter. Next one, if you consider in this here, if M1 is equal to 0.1 molar if they given, this is called as here decimolar solution. This is called as, dear students, decimolar solution, that is 1 by 0.1, 1 by 10, that is 0.1. For example, if the molarity is given 0.01 molar, this type of solution is known as here centimolar solution. because sometimes they will ask us to calculate the weight of the solution which is having the centimolar solution of present in 100 ml of the solution. If they are given the molarity centimolar, if they given, that means we have to consider m is equal to 0.01. Next one, if the molarity becomes here 0.001 molar, this type of solution is here millimolar solution. Millimolar, molarity, it is also nothing but here a molar, we can represent in terms of short form, it is a molar. Next one, for example, if you want to calculate for the neutralization, that means here m1 value also is given, its volume becomes v1, m2 also is given and its volume becomes v2. Then they will ask us to calculate the resultant molarity of the particular solution will be like this. If you want to calculate, then m is equal to, we are having the formula m1 v1 plus m2 v2 is divided by v1 plus v2. This is the formula for resultant molarity of the solution. That indicates here m1 v1 m2 v2 all the values are given. Then this formula you can't use, because if they are given the three values, fourth value you are going to calculate, but here entire data is given m1 v1 m2 v2. Then finally this is comes under, dear students, resultant molarity of the solution. Resulting or resultant molarity of the solution. Resultant molarity of the solution, if they ask us to calculate, then we have to use this formula. This is capital M. Dear students, this is about molarity, is very important. And the next one is normality. Normality is not given in our CBSE, but competitive level is very important, represented here capital N. Normality, how to define here? The number of gram equivalents which is dissolved in 1 liter of the solution. The number of gram equivalents is dissolved in 1 liter of the solution is known as here normality. Normality generally it is represented N. N is equal to N is divided by volume in liters. Sir, both are same? No sir, no. It is N indicates here number of moles of solute. Number of moles of solute. But what N indicates here, dear students? N is equal to here number of gram equivalents. Number of gram equivalents. Please try to understand the difference between here this N and this N here. Now how to write this formula? N is equal to now weight is divided by, how to calculate number of gram equivalent? Weight is divided by gram equivalent weight in terms of, I am writing milliliters, volume 1000 divided by volume in milliliters. This is the formula for normality. Sir, how to calculate here if they are given the normality here? Gram equivalent weight, how to calculate? This is only very important here. Gram equivalent weight is equal to gram molecular weight divided by N. Here N, which is indicates here the valency factor, very important, dear students. N indicates, dear students, here valency factor. Understand? For acids, we already discussed in the redox reaction, N indicates their valence factor. For acids, we have to use the term, it is called as here basicity. For bases, we are using the term, it is acidity. The number of replaceable of H plus ions from one molecule of the acid is called as acidity, basicity. The number of replaceable of one OH minus ion from the one molecule of the acid, that is called as acidity. Now for salts, how to calculate? Already we know total positive or total negative charge. For in case of redox reaction, if you take it here, for oxidizing agent or reducing agent, same. Total number of electrons gained or lost, that is total electrons gained or lost. Total electrons gained or lost. Simply we have to tell it is change in oxidation number. Simply we can call. This is the way we have to calculate gram equivalent weight. Now if we take it here, the same formula. Here also same, N which stand for here same 0.1 normal, that is decinormal. 0.01 this is centinormal. Here milli normal is common only. Here also the same thing, N1 having the initial normality, its volume becomes V1. The same after it dilute. Then what will happen here? Normality will be changing from N1 to N2 and volume becomes V1 to V2. Then we are having the relation, okay, N1 V1 is equal to N2 V2. This is the formula. Here also the same thing. If they ask us to calculate resultant normality, here also N1 V1 plus N2 V2 is divided by V1 plus V2. This is the very important formula, dear students. Please don't forget. And very important, that is known as here the relation between molarity versus normality. Molarity versus normality. Very important, dear students. Okay, now generally I am writing here normality is equal to, okay, small n into capital M. This is the very important, dear students. Please don't forget. Normality is equal to N here stands for it's the same thing here, the valency factor. Valency factor. Okay, next one. M indicates here molarity, already we know. Understand? N indicates here molarity of the particular solution. Then for example, if they ask us to calculate here, okay, what is the normality of, okay, for example, question if they are given, the normality of 0.4 molar H2SO4 solution is, if they ask us to calculate like this, simple, N is equal to small n into capital M, already we know the formula here. Okay, now N is equal to, if given here how much, dear students, molarity 0.4, here N value how much here, the number of replaceable of H plus ion from one molecule of H2SO4 how much, dear students, 2. Okay, if they replace here 2H plus, then what will happen here, 2H plus SO4, 2 minus, then what will, how many replaceable of H plus, dear students, here 2, that implies here N is equal to 0.8 normal. This is the way we have to calculate. Okay, if they are given the molarity, how to calculate normality with the help of this is the formula. Okay, next one comes under, okay, after normality we are having the one, this is called as here molality. Molality small m. This is the molarity, dear students. Please, okay, don't forget, this is the molarity, this is the molality. The small m, that is capital M. Molarity, how can you define? The number of moles of the solute which is dissolving 1 kg or 1000 grams of the solvent is known as here molality. Same, m is equal to n is divided by capital W in grams. Capital W in grams. Okay, don't forget the students here, okay, in the formula. Okay, sir, what about this one here, weight of the solute here, they don't forget, dear students, here are the weight of the solute, a gram equivalent, here weight of the, okay, n divided by capital W in kilograms. Here forgot units of this one here. Okay, if you want to write here units, n indicates gram equivalent, gram equivalents, volume in liters. This is the units for the normality. Here also I am writing here small m is equal to, here this is called as solvent, it's not a solute or solution. Weight is divided by gram molecular mass into 1000 is divided by capital W in grams. Okay, now I can write it here according to our NCERT textbook here, W2 is divided by W1 gram. This one indicates here the weight of the solute, W1 which indicates here, dear students, the weight of solvent. Please, okay, careful with the, okay, this parameters W1 and as well as W2. This is solute and this is solvent. But according to definition, what I said, the number of moles of the solute is dissolving 1000 grams or 1 kg of the solvent, but not a solution. That is known as molality. And the units of this one, molality becomes here, okay, number of moles as usual. Okay, weight in what, my dear students, kg. Okay, moles per kg. Now will it depends on temperature? Okay, here normality also depends or not, because there is a volume factor is there, here temperature is dependent. Then what about here duration? Okay, temperature is independent because there is no volume factor. Because of that only the molality of the solution is, okay, independent on temperature, there is no volume factor. This is about here molality. Okay, next one comes under, okay, one more, okay, concentration, that is 8th one, that is called as here mole fraction. These all concentration terms are very important, dear students. Please, you have to refer everything. Mole fraction, generally mole fraction represent with here capital X. Okay, it is defined as the number of moles of the, okay, components Okay, to the total number of moles of the components in the solution is known as here, okay, mole fraction. I repeat, the ratio of number of moles of the components to the total number of moles of the components in a solution known as mole fraction. Generally can represent here, if you take it here x1 is equal to here n1 is divided by n1 plus n2, you can take it here. If you take it for example x2 is equal to n2 is divided by n1 plus n2. If for example if you take it, this is the okay solvent, then you can take it total number of moles of the solvent by total number of moles of the solution. Here solute divided by okay solvent, okay solution. Next one, what is the sum, sir? If the x1 plus x2 is equal, what will happen here? n1 divided by n1 plus n2 plus n2 divided by n1 plus n2, both LCM is like this. What is the formula here? x1 plus x2 is equal to finally it is 1. This is the very important expression. Next, will it okay units anything is there, dear students? Here units no, because moles by moles both cancel here, no units. Next one, what about here? Temperature dependent or independent? Number of moles, if you increase the temperature, number of moles will not change. That's why okay it is independent on temperature. Okay, this is about mole fraction. Next one comes under here, ninth one, okay, formality. This also not given in okay our NCERT, but competitive also very important. Formality it is indicates here the number of okay gram formula units which is dissolved in okay 1 liter of the solution is known as here formality. F is equal to n is divided by volume in liters. Here n indicates number of gram, okay, number of formula units. Then you can write it here. Then F is equal to weight. Understand? Weight is divided by gram molecular weight into 1000 is divided by volume in milliliters. Volume in milliliters. Sir, it is exactly resembles like molarity formula, sir. It is molarity formula. Okay, M is equal to same. Okay, if you take it here, this especially this formality it is applicable for the ionic compounds. Okay, if the for example if you take it here volume or okay this one will be equal, then finally what will happen, dear students? Molarity of the solution which is equal to okay formality of the solution. It is mainly applicable for the ionic solutions. Next one, okay, next one units here, gram formula units per liter. Units if you take it here, gram formula units per liter. This units. Next one, will it depends on temperature, dear students? Yes, obviously volume factor is there. It is depends on temperature. Please note down, dear students, here. Okay, everything I am writing, enter all the concentration methods here. Which one is the okay is one of the many times they ask in a competitive exam. Which of the following concentration of the solution is temperature dependent or temperature independent? Okay, now I am writing here temperature dependent and temperature it is okay independent. Okay, now if you take it here, what are the temperature dependent, students? Volume factor, volume percentage, sorry. Next one, mass by volume percentage. Next one, molarity. Next one, normality. Next one, okay, formality. Next one, which one is the temperature independent, dear students? Okay, mass percentage. Next one, okay, volume percentage depends. Next one, okay, molality. Next one, mole fraction. This is comes under here okay temperature independent. Please you have to take care of this one because it is very important, dear students. Don't forget. Okay, up to here please note down and you can continue. Okay dear students, next we can continue after concentration of the solutions. We are having very important thing, that is solubility. Okay, next okay, this is very important. What is meant by solubility? Generally we know it can be soluble, okay, in particular solvent, that is called as here solubility. Generally how to define here? Okay, solubility, the maximum amount of the solute is dissolving, okay, is dissolving 100 grams of the solvent, or you can take it maximum amount of the, okay, solvent, that is known as here solubility. The maximum amount of the solute is dissolving, okay, solute or solvent, that is known as here solubility. Okay, now generally the solubility, some factors which is affecting, already we know, that is main, what type of solutions we have to take it, that means here, okay, solubility of solid in liquid, solubility of, first case, solid in liquid type of solution. Next one here, gas in liquid type of solution. We are having the one law here we can discuss, that is called as here Henry's law. Henry's law. Understand? Okay, now generally this solubility, okay, which is mainly, okay, we have to take it in two different types of solution. One is known as solid to liquid, solid in liquid type of solution. Next one, gas in liquid type of solution, that is Henry's law. First of all, we can consider solid in liquid type of solution. If we consider generally, okay, I am considering this is, already we know, just I am taking some water here, okay, this is I am considering water, just I am adding here some, okay, sugar in liquid type of solution. Generally it is mainly based on, okay, and mainly it is comes under here, okay, like dissolves like principle. Like dissolves like means polar solute can be dissolved in the polar, okay, solvents, and non-polar solutes can be dissolved in non-polar solvents. If any compound is completely soluble in particular water, that means here both are having the, okay, similar properties, okay, or we have to follow like dissolves like formula. Already we discussed in this one here about water, due to the presence of, okay, next one, intermolecular hydrogen bonding, and as well as more, okay, this one polarity nature, even covalent compounds also are soluble in the water. Actually it is comes under covalent compound here, non-polar solute, but it is dissolved in the water due to the presence of here intermolecular hydrogen bonding, due to the interaction between the water versus sugar will be the same, that's why sugar is soluble in the water. After just you put the sugar, after some time what will happen? Initially it is a sugar, it is solid state, the solid state will be leave into the water and are disintegrates into the water, and after some time we are observing a clear solution of the sugar, Okay, now generally if you take it this one, next one some, okay, this is comes under here nature of the solute, and as well this one solid and liquid type of solution, generally which is affecting on some factors, nature of the solute and solvent. Next one, temperature effect. Next one, pressure effect. This is comes under nature of solute and solvent. Okay, now what is the principle we have to follow here? Like dissolves like dissolves like. Polar can be dissolved in polar solvent, non-polar solute dissolved in non-polar solvent. Okay, next is the, okay, effect. First factor this is. Next one comes under here. Sir, what about the temperature effect, sir? Okay, now temperature, generally if you raise the temperature, the solubility, what will happen? Some, if you always it will not be decrease the solubility, always it will not be increase the solubility, but it's based on the some compounds, it will be, okay, the solubility nature will be mainly depends on the temperature. For example, if you take it here, potassium nitrate, okay, next one if you take it here, KCl or, okay, or NH4Cl, okay, the solubility is increases with raising temperature. The solubility of potassium nitrate, KCl, NH4Cl is increases with raising temperature. Next one if you take it here, the serous sulfate, okay, nonahydrate, 9H2O, okay, the solubility is decreases with raising temperature. Just have check it, in all the compounds will not be increase the solubility while increase the temperature. Understand? Next one here, what about dear students here, if you take it here, NaCl, common salt. The solubility of NaCl remains same while increase the temperature. This is the, just have check it here. Solubility here increases, solubility here decreases. Here solubility is remains same. That means here all the compounds are not completely soluble in the water with a particular manner. Okay, if you increase the temperature. Okay, it's a different example for that. Okay, temperature effect. Next one, if he comes under here. Okay, next one, what is the effect of the pressure on solid in liquid type of solution? Already we know solid, liquid and as well as gases. If you take the solid, if you compress here, it won't compress because due to highly intermolecular attraction forces here. That's why solids, the effect of the pressure will not be effect on solids and liquids. It is only present in terms of gaseous molecules are there, or gaseous reactions are there, because gaseous molecules are highly compressible, whereas here highly incompressible. That's why pressure effect will not be alter in type of in this type of solid and liquid type of solution. Okay, this is solid in liquid. Next one comes under here, gas in liquid type of second, that is gas in liquid type of solution. Gas in liquid type of solution, very important dear students. Gas in liquid, generally what will happen? Solubility. Okay, very important, just you have to take it here. Nature of the solute and as well as solvent, already we know. If you take the carbon dioxide is nicely soluble in the water. Okay, nicely soluble in the water, especially we are using in soft drinks and as well as soda water. Okay, now the solubility of gas, very important, temperature effect. Okay, the solubility of gas decreases with rise in temperature. Very important point this one. The solubility of the gas decreases while increase in temperature. This is very important. Next one, if you take it those gaseous solutions which forming ions. Okay, ions such as here ammonia and as well as HCl. Ammonia and as well as HCl are more soluble in the water when compared to organic solvents, because ammonia also can forming the ions here, HCl also can be forming the ions. Because of that only those solutions are those reactions which are having which form the gases which forming the ions are more stable or more soluble in water when compared to organic solvents. Next one, gas in liquid type of solution, we are having one law that is known as here, dear students, very important. They given the quantitative relation between the pressure of the gas versus mole fraction here. Now that law is known as here Henry's law. What is Henry's law, dear students? The is given the relation, the partial pressure of the solution in gaseous phase is directly proportional to the mole fraction of the solution. Very important. The partial pressure of the gaseous solution in gas phase is directly proportional to its mole fraction at constant temperature. Then what will happen here? Then pressure P is equal to now I am writing here one of the constant, that is called as here KH into X. Here KH, which indicates here KH is called as here Henry's law constant. Henry's law constant, dear students, very important here. But Henry's law constant is not comes under universal constant. It is it is only for the constant for this one. This Henry's law constant, this KH value which depends on nature of the gas, and as well as here temperature. Very important. These two factors which is depends on KH here. KH depends on nature of the gas and temperature. If you same here, the KH value is increases while increase in temperature. Sir, what is the condition, sir? That means here the pressure is not too low, the temperature is not too high. Next one, whatever you are taking the gaseous solution should not be dissociate. That is the condition for Henry's law. Next one, very important for the NCERT pattern. This is applications. What are the applications? Many times they ask, write the two applications for the Henry's law. First, what is first application? The solubility of carbon dioxide. Solubility of this carbon dioxide in soft drinks and soda water. This is very important, dear students. Soft drinks and soda water is more. Am I correct or not? the solubility of, for example, whatever you are drinking, soda water or soft drinks, maximum amount of carbon dioxide. Okay, then before you are opening that lid, if you shake it, then what will happen? Every carbon dioxide, okay, every liquid present in the bottle will come out. The solubility of carbon dioxide in soft drinks and soda water increases at a high temperature, at a high pressure. For example, how the marble which is settled towards up in the soda bottle, okay, if you are continuously, okay, sending carbon dioxide gas into the soda bottle, then what will happen? The carbon dioxide gas is completely, the carbon, for example, if you take it here, okay, the carbon dioxide gas is completely soluble in the, initially what is there, dear students, this is the water. Okay, then after you are passing carbon dioxide gas is completely soluble in the water, then excess amount of the pressure is there, then what will happen? This excess amount of the pressure will be pulling the marble towards up. Then finally what will happen? At a high pressure the marble will be settled, okay, to in the, okay, marble will be settled towards the, okay, towards up in the soda bottle. That means solubility of carbon dioxide in soft drinks and soda water increases, okay, at high pressure. This is the very important. How the marble will be settled? That means due to the more pressure effect. Next one, second application here, very important. Generally the partial pressure of the oxygen while you are going towards up higher altitudes such as mountains, such as if you know, they will be carrying some oxygen cylinders. Then the partial pressure of the oxygen, okay, is decreases, okay, when compared to the ground level. If the partial pressure of the oxygen decreases, then what will happen? The amount, the concentration of the oxygen in the blood, what will happen, dear students? Decreases. If it decreases, what will happen? The amount of the, okay, what is the oxygen in the blood, then what will happen? The people become weak and unable to think clearly. Okay, then such type of condition is known as here, the symptoms is known as here anoxia. Very important here, anoxia. The one more time I am explaining. The partial pressure of the oxygen is decreases when you are going towards higher altitudes when compared to the ground level. So that what will happen here, the concentration of the oxygen in the blood will be decreasing. Then if it happen, okay, if it so happen, what will happen? Okay, then, okay, the people will become weak and unable to think clearly. Such type of symptoms is known as here anoxia. This is the very important. These are the two conditions which is application which comes under Henry's law. This is very important. Okay, next one comes under here. Okay, what is meant by here? Vaporization. Now let me explain about, okay, Raoults law. Okay, before that one I am explaining some here. Vaporization. Vaporization means already know the process in which the conversion of liquid into vapor at given temperature, that is known as here vaporization. Okay, next one here called as rate of evaporation or rate of vaporization. Rate of vaporization, rate means here the number of molecules which escape from the liquid, okay, per second is known as here rate of vaporization. This rate of vaporization mainly it depends on, okay, mainly depends on the temperature and as well as the surface area and as well as flow of air. If the surface area is more vaporization will be. Next one, if you increase the temperature, what will happen, dear students? Evaporation or vaporization will increase. That means here the temperature which is directly proportional to, okay, vaporization and which is directly proportional to here surface area, okay, and which is directly proportional to here, okay, flow of air. This is very important. Flow of air, this is the condition. If you temperature, if you vaporization, when in which cases will increase? If you increase the temperature, vaporization will increase. Okay, surface area increase, vaporization increase, flow of air also. Okay, if take it here, then vaporization also will be increasing. Next one comes under very important, that is called as here vapor pressure. Vapor pressure. Okay, what is meant by here vapor pressure? For example, if you take it here on small container. Okay, vapor pressure is the best example. What my dear student, pressure cooker. Okay, now if you take it some liquid here, the pressure exerted by the liquid of the surface over the liquid, correct? Then these vapors of the liquid, are in equilibrium with okay, this liquid. That means simply you have to represent here vapor pressure. When the water will get evaporate, the vapor pressure of that water which is equal to the atmospheric pressure, then what will happen, dear students, the vapor, okay, the water will be, okay, water will get evaporate. Then what you are observing here, vapor pressure, the pressure exerted by the vapors of the liquid, okay, over the liquid surface, then these vapors of the liquid which is equilibrium with this liquid is known as here vapor pressure. This is the very important, dear students. Next one comes under here lowering in vapor pressure. Generally it is represented with here delta P. What is meant by lowering in vapor pressure? Just I am taking here two containers. In that one container I have considered only pure liquid, that is called as a pure solvent. I am taking pure solvent. Okay, this is A. Next one, okay, one more container I am taking here. I am considering this is the water and I am adding some solute. Here this is called as here solution. Vapor pressure of solution here. Just have check it, dear students. Applying the same temperature among these two container, which one having the greater vapor pressure here? If you apply the temperature here, then what will happen, dear students? This water molecule is completely absorbing the heat energy, and slowly what will happen, dear students? This water molecule gets evaporate. But in case of come to the here container B, if you increase the same temperature, then what will happen here also? Some liquid molecules are there, water, and some of the solvent molecules are replaced by the solute molecules. Okay, this is the solvent, this is a solute. What will happen? At the moment you are increasing the temperature, all the solute particles will be holding the water molecules very tightly. Then what will happen? Due to this less vaporization or more vaporization, dear student, less vaporization, that pressure is called as here less. Due to this is called as here low vapor pressure will be. That is known as here lowering in vapor pressure. Due to the presence of non-volatile solute particles in the solution, these after you are increasing the temperature also, this solute particles is completely holding to the solvent molecules. Okay, then this water, okay, these solute particles can't make it evaporate these solvent particles. So what will happen? The vapor pressure will be decreasing. That decrease in vapor pressure is known as here lowering in vapor pressure. Very important, don't forget. But here, what in this case, what will happen, sir? Here there is no solute particles. At the moment you are increasing the temperature, all the solvent molecules absorbing the energy, kinetic energy will increase. Next one, vibration also increasing. Then slowly the water will get evaporate. Now, but in case here very less evaporation due to the presence of non-volatile solute or okay solute particles is present. Non-volatile solute is present. Now I can represent here okay del P is equal to, in the definition, P naught minus P. Okay, here P I can write it here PS. Sir, what is here del P? Del P, which is indicate lowering in vapor pressure, I can define as the difference. Okay, the difference between the vapor pressure of the pure solvent to the vapor pressure of the solution is known as here lowering in vapor pressure. Next one comes under here relative lowering in vapor pressure. Generally it is represented here del P is divided by P naught. In the definition itself there, formula, it is the ratio of okay the lowering in vapor pressure to the vapor pressure of the pure solvent is known as relative lowering in vapor pressure. Generally it is represented here del P. What is the value here? P naught minus PS divided by P naught. This is the formula for RLVP. Now let me start here. What is Raoults law? Here also the same thing. Okay, Raoults law. Here also this Raoults law also will be okay. We have to discuss in terms of here two types of systems. One is comes under same liquid in liquid type of solution or liquid in liquid system I am taking here. This is the case one, and one more, that is solid in liquid system or solid in liquid type of solution here. Okay, now let us start with a very important, this is a liquid. Okay, first case 1 I am taking. Okay, liquid type of solutions or system. First of all, what is here Raoults law with respect to liquid or volatile liquid solutions. Okay, now I am explaining here the vapor, the partial pressure of the solution. Okay, what I am taking, dear students, the partial pressure of the solution, the partial pressure of the solution is directly proportional to the mole fraction of the solution. Generally I am considering a small derivation part is there here. Okay, I am considering two types of solution A and as well as B. Its partial pressure becomes here PA, then its partial pressure become, dear students, PB. Now I can consider here, this is called as a PT. PT is equal to total partial pressure is equal to PA plus PB. Initially how to write here? PA is equal to PA naught into XA, then PB is equal to PB naught into XP. According to Dalton's law of partial pressure, you have been studied in gaseous laws, Gay-Lussac's law, Charles' law, Bowles. Okay, next one. Dalton's law for partial pressure. According to Dalton's law of partial pressure, according to Dalton's law of partial pressure, then Dalton's law of partial pressure, what will happen, sir? Okay, the total partial pressure is equal to the sum of the partial pressures of individual gases or individual solutions. Now let me take it here. PT is equal to, then what I am taking here? Okay, P total is equal to PA. PA value what, my dear students? PA naught into XA. PB value, dear students, PB naught into XB. I am taking the two solution now, I can take it here. Then I can write it here. Already we know mole fraction, the sum of the mole fraction is equal to, so unity or not, dear student? X1 plus X2 is equal to 1, or XA plus XB is equal to 1. I can take it here from XB is equal to 1 minus XA, just I am substituting here. Then total partial pressure is equal to, I can write it here, PA naught into, I can write it 1 minus XB, or I can take it here, XA is equal to 1 minus XB, or XB is equal to 1 minus XB, anything you can consider. Okay, plus PB naught into XB. Then what will happen here? Same, PA naught minus PA naught into XP plus PB naught into XP. Then I am taking as XP is the common here. Then I can write it here, PA naught plus XB if you taken as common here, PB naught minus PA naught. This is called as here, dear students, our expression for Raoults law. The total partial pressure of the solution which is directly proportional to mole fraction. Okay, now just I am comparing this formula with slope. Y is equal to here C plus X into here, dear students, mx plus C. Then m is equal to slope, m is equal to, dear students, PB naught minus PA naught. Okay, we will be having here two types of slope here. This is I can consider here positive, and this one I can consider here negative slope. This is a positive slope, this is the negative slope. Then here what is the condition? If the PB naught value which is greater than PA naught value, this is comes under positive slope. But in case of, if you take it here, the PA naught value which is greater than PB naught value, which is comes under, dear students, this is negative slope. Okay, next one comes under here. Okay, now generally according to Dalton's law of partial pressure, total partial pressure which is equal to mole fraction of the solution. Generally I can write it here. Now partial pressure is equal to I can consider here YA into total pressure. Understand? I can consider this is a PA. Then you can consider PB is equal to here YB into PT. No, sir, here you mentioned here XA, XB, sir. What about here YA, YB? Here XA and XB, which indicates the mole fraction in the liquid solutions. But in case of here YA and YB, which indicates, dear students, okay, the vapor pressure which is present, the partial pressure which is present in gaseous phase. Very important here. YA and YB, which indicates what were, dear students, here? The partial pressure in gaseous phase or gaseous phase. This is the very important. But in case of this XA and this XB indicates here the mole fractions. Sorry, partial pressure is not here. The mole fraction is not a partial pressure, dear students. It is a mole fraction in gaseous phase. This is a mole fraction in liquid type of solution or liquid phase. Okay, dear students, please be note down. You can continue. Okay, dear students, so far we discussed Henry's law completed, and as well as Raoults law. Raoults law for the system 1 we completed here, liquid and liquid type of solution. Just I am revising the partial pressure of the solution which is directly proportional to mole fraction. Then finally what we wrote, dear students, Pt is equal to Pa naught plus, okay, Xb into Pb naught minus Pa naught, and conditions also, slope also we written there. Okay, there please careful with the terms Xa and Xb, which indicates here the mole fractions in liquid type of solution or in liquid phase. But in case of, if we take it here, Ya and Yb, which indicates, dear students, with the mole fractions in gaseous phase. With respect to slope also we discussed. Next one, just if you draw the graph between that one, okay, then what will happen here? Okay, we can consider here, this is the vapor pressure. I can consider this is a mole fraction. I can consider this is Xa is equal to 0, here Xa is equal to 1, here Xb is equal to 1, Xb is equal to here 0. Okay, here 0, here 1, here 1, 0. Don't get confused, dear students. Okay, next one, if you take it like this, what will happen? This is, I can consider this is Pa naught. This is, I can consider it is Pb naught, and this is, dear students, okay, total. Okay, Pa naught, I can write it here, Pa is equal to Pa naught into Xa. Now I can write it, this is Pb is equal to Pb naught into Xp. This is comes under, dear students, P total. P total is equal to Pa plus Pb. Pa is equal to how much? Pa naught into Xa plus Pa naught, Pb naught into Xp. This is for, okay, liquid type of solutions. Okay, next one comes under here, case 2. Okay, case 2, we can take it here, solid in liquid type of solutions here. This is a normal, okay, solid in liquid type of solutions or system, the same thing. Okay, the relative lowering in vapor pressure of the dilute solution containing non-volatile solute, which is equal to the mole fraction of the solvent. Generally we have to consider the relative lowering. There is no any derivation here, you can write it directly. The relative lowering in vapor pressure, relative lowering already we know, dear students. Okay, del P by P naught, correct or not? That is equal to P naught minus Ps divided by P naught, which is equal to mole fraction. Okay, I can consider here mole fraction of the solvent, I can consider 1, no problem here, mole fraction of the solvent. This is in solid in liquid type of solution, dear students. This is the about here, okay, case 1 and as well as case 2. This is solid and liquid. What I said here, the relative lowering in vapor pressure of dilute solution containing non-volatile solute. Whatever you are taking a solute, it must be, it should not be non, okay, it should be non-volatile, it should not be volatile in nature, should not be evaporation in nature, okay, which is equal to mole fraction of the solvent. That is okay, other statement of Raoults law. Got this, dear students? This is about, okay, solid in as well as liquid type of solution, very important. Okay, next topic is ideal and non-ideal solutions. Ideal and non-ideal solutions. Okay, just you have to listen, dear students. Here already you studied in the gaseous state what is ideal gases, non-ideal gases, or it's also called as real gases studied. Here also the same thing. Now let me start with here. First of all, what is ideal solutions here? Ideal solutions. Okay, let me start. Ideal solution means the solution which obey Raoults, okay, Raoults law. Solutions, okay, which obeys Raoults law, correct or not, dear student? The solution which obeys, okay, Raoults law, okay, such type of solution is known as ideal solutions. Ideal solutions. Okay, now in case of ideal solutions are there, sir, then what are the conditions, sir, and what is the graph which is related to that one? Ideal solutions. Okay, now I can write here what are the conditions for ideal solutions here. Ideal solution conditions, mainly this ideal and as well as non-ideal solution, which is completely based on the interaction between, okay, let me take it here, okay, interaction between AA and as well as BB and as well as here AB interactions. Okay, now but in case of here, okay, ideal solutions are there, sir, what about their interactions, sir? The AA interactions which is equal to BB interaction is equal to AB interactions. This is a very, very important. Okay, this is the first condition here. Understand? AA interaction is equal to BB interaction is equal to AB interaction. Okay, now this is the first condition. Next one, and the second condition, okay, now the change in enthalpy, okay, mixture which is equal to 0. This is a very important. That means here, okay, no heat energy is evolved or as well as absorbed. Okay, the entire heat and the entire system of the heat energy becomes here is equal to should be 0 and comes under here third condition. Okay, del V, okay, the mixture of the del V becomes is equal to 0. Here also, okay, the change in volume, okay, of the mixture is equal to, it should be 0. That is the condition. AA BB interaction is equal to AB interaction, delta H mixture is equal to 0 and delta V is equal to 0. And what about here partial pressure, dear students? Here the same, the PA is equal to PA naught into XA, the same thing, and here also PB is equal to PB naught into XB, the same thing. Okay, next one, total partial pressure also is the same thing, PET is equal to PA plus PB, same. So okay, for ideal solution these are the conditions. Okay, next one, if you take it the same, okay, same like already we drawn here, just again I am showing here. Okay, now this is the vapor pressure and this is the mole fraction. I can consider XA is equal to 0, here XA is equal to 1, xp is equal to here 1, xb is equal to 0. Okay, in case of ideal solutions, then how like I am taking, dear students, this is okay, this one I can mention here, this is PA naught, this is PB naught, this is the total partial pressure. PT is equal to PA naught into XA plus PB naught into XB. But in case of here PT, okay, PA naught, how can you write it, dear students? PA is equal to PA naught into XA. But in case of here PB naught, if you take it here, PB is equal to PB naught into XP. This is the graph for ideal solutions. Okay, now PA, PB, everything is equal. Okay, next one, PT, total partial pressure, PA naught into XA plus PB naught into XP. And what are the examples which comes under, okay, this okay, ideal type of solutions? If you take it here, N-hexane and N-hexane and N-heptane, N-hexane and N-heptane. Okay, next one, if you take it, okay, chlorobenzene and bromobenzene. This is a general example for the ideal solutions. Comes under here, second one is very important, that is I can write it here, case 2. Okay, this is the ideal solution. Next one I can consider, this is non-ideal solutions. Non-ideal solutions. Sir, what is meant by here non-ideal solution? Already written here. Ideal solution means, dear students, solution which obeys, or those solution which obeys Raoults law is known as at all concentrations. What is, dear students, here? At all concentrations and temperature is known as your ideal solution. But comes under here non-ideal solution. Okay, those solutions which do not obeys Raoults law. Such type of solution is known as here, okay, non-ideal solutions. Non-ideal solution is the same concentration, if you take it here, pressure also. But in case of non-ideal solutions are there, sir, what are the conditions, sir? Condition for the non-ideal solutions. Okay, first condition already we know. Okay, AA interaction, BB interaction, everything is equal. But in case of non-ideal, okay, AA interaction, okay, is not equal to BB interaction, which is not equal to AB interaction. This is the first condition, dear students. AA BB interaction which doesn't equal to AB interaction, and comes under everything is reverse, dear students. Okay, here PA is not equal to PA naught into XA, sorry, PT. Okay, next one. Here I can write it here, what is, dear students, PT here, mole fraction, no, okay, XA, the same thing, okay, XP. Here also XA. Next one, PB doesn't equal to here PB naught into XP. Okay, this is the condition, second condition. Next one comes under here, third condition, delta H mixture is doesn't equal to 0. Here also del B mixture is doesn't equal to, dear students, 0. This is the condition for non-ideal solution. Generally this non-ideal solution which behaves or which okay deviate which deviate from the Raoults law, such type of okay solution called as a non-ideal solution. Okay, there is a deviation. This non-ideal solution can be deviated to non-ideal solutions, okay, deviate from Raoults law. This is a very important, dear students. Okay, deviate from Raoults law. How many conditions, dear students, here? There are two types of deviation will be. One is comes under positive deviation, and the second one is comes under here negative deviation. Okay, now let us start. Okay, what is here? I can take it here, case 1. Okay, positive deviation. Positive deviation, non-ideal solution, dear students. Okay, same. Positive deviation, that means here, what are the conditions, dear students? Condition for positive deviation. The first condition is, okay, PA, first of all, what is the interaction if you take it here? AA interaction, AA and as well as BB interaction, BB interactions which is greater than AB interaction. This is the first condition, and the second condition here, PA which is greater than that of PA naught into XA, and PB which is greater than PB naught into XP. This is the second condition. Next one comes under, sir, what about here? Del H mixture. Del H mixture which is greater than 0. Here also same fourth condition, del V mixture which is greater than 0. This is the conditions. Okay, next one, what are the examples? I can take it here first. First of all, we can draw the graph. Okay. Now for the positive deviation, how the graph will be, dear students? Please be noted down, is very very important here. Understand? I can consider this is the same vapor pressure. I can take, so this is the mole fraction. Same I taking XA is equal to 0. Here XP is equal to 1. Here XA is equal to 1. Here XP is equal to 0. This is the mole fraction versus vapor pressure I can consider. Okay. First of all, what I am writing here, the same dV without deviating. First of all, I am writing here, drawing the, okay, this is called as here, you can take it here, PA naught. This is I am writing, this dotted line which indicates here, okay, ideal solution. Then what you have written, sorry, this is comes under non-ideal, no sir. Okay, now how it is deviated, then I will explain. This is initially ideal solutions. Understand, dear students? This is PA naught, and this is comes under here, dear students, PB naught. Okay, now positive deviation, how it will be, dear students? Okay, towards positive. This is increase, positive deviation. This is positive, and this is positive. That means increase or not, dear students? Increase. Okay, now this is comes under, okay, PT which is greater than that of PA naught into XA plus PB naught into XP, because greater, everything is greater only here. Now you can consider what is the PA naught value, sir? PA naught I am writing here, okay, PA which is greater than PA naught into XA. This is the positive deviation of okay, partial pressure PA naught. Now what about PB naught, sir? You have to write it. Please don't write in the dotted lines, because this is the ideal solution. It deviate, non-ideal solution which deviate from the ideal solution. How you have to express? First of all, you have to put it. This is the ideal solutions. Okay, ideal solution. What happened here? It is deviated from Raoults law. That is, it is called as a non-ideal. Positive means increasing. You can consider PB which is greater than PB naught into XB. This is the graph for, okay, positive deviation, okay, for non-ideal solution. Next one, what are the examples which comes under, sir? Okay, positive deviation. Understand? Positive deviation, if you take it here, example, alcohol, okay, ethanol and water. Okay, next one, if you take it here, methanol, CH3, OH and water, if you take it. Next one, if you take it here, CCl4 and benzene, and you can take it here, CCl4 and toluene. You can take it CCl4 versus okay, chloroform. These are the example for the positive deviation, that is case 1. Next one comes under, dear students, very important, that is case 2. Okay, case 2, what you said there? This is a negative deviation. Negative deviation, everything what we wrote, okay, here everything becomes reverse. Okay, now what is the, dear student? First condition, negative deviation. Okay, the AA interaction, okay, and the BB interaction which is less than that of AB interaction. That means here AB interactions are more stronger than AA and as well as BB interactions. Okay, AB interaction. Okay, next one, second condition, if you take it here, the negative deviation, that means PA which is less than that of PA naught into XA, and PB which is less than PB naught into XB. Okay, obviously we know, then PT, total pressure, which is less than that of PA plus PB. Am I correct or not? Next one comes under, what about the third condition, sir? The same, delta H mixture which is less than 0, because it is, what is the, dear students, here greater than 0, here greater than 0, here less than then change in volume of the mixture which is less than 0. Here delta H is which is less than 0 means what type of reaction, dear students? Here this is a exothermic reaction. Exothermic reaction. What about here, dear students? This process becomes endo. Now let me draw the graph between here mole fraction versus vapor pressure. Graphs are very important, dear students, don't get confused. Okay, if you understand, you can easily do it. Okay, now you can take it, this is the vapor pressure and this one I can consider mole fraction. Okay, now initially what I am writing, same like okay, ideal gas I am writing, ideal gas, this is this, next one, this is ideal gas. I can mention here, this is PA naught and this is PB naught. I can consider this is XA is equal to 0, XB is equal to, dear students, 1. Here XA is equal to 1, XB is equal to 0. Understand? Next one, negative deviation. Negative deviation, how it will come, dear students? The same thing. Okay, PA naught I am writing here. Okay, negative. This one, if you take it, that is the positive, increasing. This is negative, decrease or not, dear students? Okay. Okay, next one. First of all, okay, take it like this. Next one. Okay, next I am taking this is okay, don't get confused. Now I can write it, this is PA curve, no, PA which is less than PA naught into XA. I can take it, this is PB which is less than PB naught into XB. And what about here, dear students? Sorry, this is okay, total, correct or not? P total which is less than PA naught into XA plus PB naught into XB. This is P total, no? Next one, what is the PB naught? Okay, this is PB naught value I am writing here, PB which is less than PB naught into XB. This is the very important. Check it here. This is the ideal solution without having the any deviation. But in case of non-ideal solution, we are having the deviation from the Raoults law. Okay, how many deviations we can? Positive deviations, negative deviation, positive deviation condition, everything I mentioned here. First you have to draw the Raoults law solution. Then after you have to increase. This is the increasing. Here also increase, this also increase. But in case of here negative, this is a decreasing curve, it is decreasing, and here decreasing curve. Okay, now already conditions also written. This is about negative deviation and comes under here examples. What are the examples? Okay, you can take it here, chloroform versus diethyl ether you can consider. Understand? Next one you can take it here, chloroform versus, you can take it here, dimethyl ketone, you can take it acetone. This is the way we have to study, dear students. Okay, now just you have to revise. Okay, this is comes under solid and liquid type of solution of the Raoults law. Okay, liquid completed, ideal, we are having those solutions which obey Raoults law called as ideal solution. Conditions I written. Okay, this is the graph without having the any deviation. Please try to note down. Okay, next one, examples I gave. Okay, here everything is becomes equal, delta V, delta X, everything becomes should be 0. This one is equal to it's respect to partial pressure. Non-ideal which do not obey Raoults law. We are having the conditions. Here AA, BB interaction is equal to AB. Here everything is not equal. Here also everything is not equal. Next, non-ideal solution, how it will deviate from the Raoults law. We are having a two deviation. One is positive, one is negative. Next one, in that positive deviation conditions, everything graph and as well as example we written. Next one comes under case 2, negative deviation. What are the interactions and its conditions and with respect to graph and some examples. I hope everyone understood, and the second part we have to continue in the next video. Thank you.